Hi, everyone. Welcome to the Heliocon seminar series. My name is Brooke Stanislawski, and as of last month, I'm taking over for Rebecca as the host, since she'll be starting her fellowship with the Department of Energy. A big thank you to Rebecca for starting up this seminar series and being an incredible host so far. I'm pleased to be the new host, and I'm looking forward to bringing some fantastic speakers for you all, starting with today and last month. So just a bit of background, the Heliostat Consortium, or Heliocon, is a 5-year research effort led by the National Renewable Energy Lab, partnering with Sandia, the Australian Solar Thermal Research Institute, and DOE's Solar Energy Technologies Office, to develop and manage a national lab-led U.S. consortium to support research, development, validation, commercialization, and deployment of low-cost heliostats for concentrating solar power and solar thermal applications. So just a few housekeeping things before we get started. The seminar is being recorded and it will be made available afterwards. Please stay muted when you are not talking and during the presentation. During the presentation, feel free to put questions in the chat to be answered in the last 10 to 15 minutes during the Q&A session. And after that, you can also unmute and ask your questions directly. So I will now introduce our speaker for today. So Mo Tian is a PhD student in electrical engineering at Arizona State University. Mo acquired his master's degree in electrical engineering from Arizona State in December 2020 and joined Dr. Yu Yao's lab group to continue his study in May 2021. His research interests include the application of polarimetric imaging technology in energy, ocean microscopy, and biomedical fields. He has been working on utilizing polarimetric imaging in various aspects of field inspection in a concentrated solar power plant at Sandia National Lab. All right, Mo, I will hand it over to you. Thank you.
All right, thank you, Brooke. Hello, everyone. So today I'm going to talk about how our research going on with the Heliostats inspection with polarimetric imaging. There are two parts. I put optical errors and mirror cracks in part 1 and the mirror soliding in part 2. So both of these parts use polarimetric imaging. There are some shared theories and device, but they are also different in the physics fundamental level. So here are a list of my co-authors, myself and Dr. Zubair Rafiq, who has graduated from my lab, and Kolop and Neil, who were working with me as master students for automation engineer, with me during going on with this whole project, and Dr. Jingbai, who's also graduated from our group, and our collaborator from Sandia have Randy, Dan, and Dave. We work with them closely, especially during the flight test at Sandia, and Julie Cielo here, who offered us a lot of initial thoughts and the planning on the flight path. So he provided me with the initial code to do that, and of course our lab PI, Dr. Yao. So this project was funded by DOE Seattle office, and it is a collaborative work with between our group at the ASU and Sandia National Labs. So before we start, I'll do a little bit overview of the whole thing. And according to the audience today, I think most of you are pretty familiar with the concentrated solar power plant. And as time goes, we notice there's problems with the daily operation and inspection of this large field because they can have cracks, they can have optical errors as the mechanical structure supporting those heliostats get loose, and they can get dirty over time because of the sand. So there's soldering deposit on them. And there are different ways, of course, to inspect all of this. A lot of state-of-art technology has been developed to counter all these kind of issues from different view. And the one we focused on is we try to integrate the polarization sensor onto this UAV, so we can do a UAV-based inspection. The benefits of that is you can do a fast and accurate scanning, take images, and they with a detailed planning, you don't necessarily need to interrupt with the field operation. So they can still be at their tracking position while the inspection is going. So a little bit of background here. we are using a special imaging technology. So when we think about light, we usually think about intensity and wavelength, or to our eyes, that's just how bright or what's the color of the light. And what human eyes cannot see is the polarization of the light. And that basically describes in which direction that the electrical field is oscillating. And of course, there's also circular polarization, which is not really used in this project. So naturally, when the sunlight passes through the atmosphere, release scattering happens, and to us, we see that the sky turns blue. But it also changes the polarization of the light. And if we are standing if we think us as the center of this coordinate system and look up to the sky, we can see a dome of the skylight. And this skylight, after release scattering, actually forms a very distinctive polarization pattern. And there are different ways to interpret this, but if we calculate the degree of linear polarization, which is a parameter to describe how linear polarized it is, if DOLP equals to 1, that means it's only oscillating at one direction. Like if we define this to be 90 degrees of our coordinate system, this is only at 90 degrees so this is a completely linear polarized, which is DOLP equals to 1. And when the light is fully unpolarized, we have this DOLP equals to 0, which is the natural light. So like sunlight itself is the unpolarized light. So at different location, different weather condition, and the way where we're standing, where we're observing, we can see different part of the sky having different DOLP. And furthermore, I introduced, they also have a different angle of polarization. But those natural features allow us to do something with the polarization of the light and using polarimetric imaging. So I'll discuss them further in later. I've divided this into two parts. The part one, I'm going to talk about the polarimetric imaging enhanced inspection, which I'm mainly talking about the optical errors and some of the results we got for the mirror cracks. And then after that, I'll talk about how we use a similar technology, but also theoretically different to inspect the soldering level of the mirrors on heliostats. So, this you already know, but when we talk about the optical arrow, there are mainly two parts. We see the tracking arrow, which is the inaccuracy of the target position and the actual position of the whole heliostat. And we also have the canting arrow, which is the misalignment of each mirror facets, because each of these heliostats usually composed of a lot of small heliostats, small mirrors. In our case, we use the one we used in Sandia heliostat. It's the 5x5. So as designed, they should form a close to a parabolic shape. Each of these mirror facets have a slight different angle to better focus the light onto the receiver of the center tower. And in previous research from the paper, we find out not just for the central receiver type, but also for the parabolic trough and linear Fresnel. As the optical arrows increase as time goes, parts get loose here and there, optical efficiency drops significantly. So a routine inspection and correction for this is quite important. And there are different ways to do this. The most traditional way, we can have a portable setup, take images, use optical models. From the papers I read, people also use all different kind of things like LiDAR, like thermal imaging, or design a efficiency target as somewhere installed on the field. But when we talk about the fastest and most non-intrusive inspection to the field, can rely on a UAV-based inspection. So this way, when you fly over the heliostat field and take images or videos, it doesn't have to interfere with the field operation, and it's a lot faster. And since there's no human involved, you also don't have to follow too many safety protocols, and don't have to stop the field. So here's the motivation. And we checked we mainly follow two research. One is led by Julius. This is the U-facet method, where they use the UAV, but instead of using polarization, of course, they use the conventional, what we call this visible cameras, and install on the UAV and take the images of a pair of heliostats. And the idea is the front and the front and back heliostats. So the target heliostat will have a reflection of its backside, which on the Sandia field, of course, is this kind of X and a little ring in the center. These features and the color is different, also very different from the sky. And when you put them in there, you can use an optical model to calculate how the image should be formed in comparison to how the image actually formed when you capture them, and find the difference between them to correct the error. And a similar concept, but using a very different target, is this Rebecca and Guangdong's approach called NEO, a non-intrusive optical approach, which they instead of using the heliostat, they use the tower, which is of course a bigger and very stable one target, and again calculate the optical model to try to form the image theoretically compared with the image actually captured. So both of these UAV-based methods, they rely on the visible camera, and they do need to detect the edges, especially when we are having. So in this example, we only see these two are starting up and looking at their tracking position. But as the field actually operates, all of these are actually at tracking position or facing up, and they can have a bunch of issues, which I'll show later. So again, this is a diagram on how the U-facet works, and for our work, we mainly follows a U-facet method, and in their case, they follow these features, calculated the center of the heliostat theoretically, and find the center of the heliostat backside, the mirror facet backside center on the image, and compare their difference and try to calculate the canting error. So this is actually a screenshot from the footage of the U-facet taken. Randy gave this to me. And you can see there are actually different scenarios that we need to deal with while we're trying to do a one-time scan over multiple heliostats. And these are not all the occasions listed, but it's one very significant one you can see here. It's called sky versus sky. This is when these two heliostats have a part of the overlaps in the image. And the problem is when they're both facing, they were both reflecting the sky. They're both blue, very similar intensity on this weather condition. You can't really tell, especially for the machine vision, you can't really tell automatically where the edge should be. So that's an issue, and to make it more faster and more automatically applicable to the field, it is important to have another method to help enhance the contrast, to help detect this edge. And so that's where the polarization imaging comes in. And before we really dive into how that works, there are some basic concepts I've already explained a little bit, but here's just to clarify. So when the sunlight pass through the atmosphere, because of radiation scattering, not only it forms the blue sky, it also forms this pattern of polarization. And if we calculate them separately, the degree of linear polarization shows this. And this is also quite intuitive because at the sunlight position, like here, right now we have the, so here we have theta as the Mo angle and phi as the zenith angle. So at this position here, when the sun position as to 200, 350 and 35, 235 degrees as Mo angle and 30 degrees zenith angle, where the sunlight direct comes in, because the sunlight is very strong, very intense, and that has unpolarized components. And the further away from it actually forms a high DOLP region. And similarly, just by recognizing this pattern, there actually works done in this field to use this pattern help with navigation. Just by recognizing this pattern of the AOP, you can locate the sun position. So how does that come in play in our work? So we're going to calculate a few things. We have this as the skylight as the input, and because we're dealing with this mirror surface, of course, this light will encounter specular reflection of the mirror surface, and not only the intensity will change a little bit depending on the material, the polarization also change, and I'm going to show you how exactly we calculate that later. We also develop a based on torrent spiral model, we calculate what the light looks like, of course, approximately in the model. What's the polarization change going to look like after you reflect off the ground, which is not a specular reflection anymore because ground is rough and has all different kind of cracks. So before we go into the technology details, we're going to introduce a little bit how we did all this test with a system. So this is a system we kind of prototype and assemble together by ourselves. And most important part here is a Lucid Triton polarization camera. Lucid is a company, Triton is the model. And it is based on the Sony sensor that is able to that has wire gratings of 4 different linear polarization gratings. And we integrate this with a Jetson Xavier NX, which serves as our microcontroller. We did all the coding and saved the images on here, so you can imagine this is a small computer. And we connect this with this is the Grimson T7 gimbal, which was available at Dan's Dave's SNDS. They offered this to us. They have this customized encoder connected to the Skyfish drone. Where there on the Skyfish drone, it has the embedded orange cube that is responsible for the wireless transmission signal onto the ground station. On the ground station, we also develop this customized UI that runs on the Jetson Xavier. Have a few functions like the live view of the what the camera is looking at, and a quick capture of the DLP just to give the operator an idea if this is a good photo or not. And we can save the image. We can by triggering the command. So this is what it looks like before the system took a flight. This was in San Diego, in Randy's lab. And in short, it can support about 15 frame per second streaming for the operator to see. And we also developed the adaptive exposure algorithm to avoid overexposure, because when you're flying over the field, you look at different part of the sky. Sometimes it gets a lot brighter than the other occasion. So the exposure has to be adjusted automatically, because obviously we cannot adjust it by our hand up there. So they can also capture the image, as I said, by triggering one of the channel, and you can tell the Jetson to save the image. So it will save the image as we desired. And a little bit details of how this polarization camera works. And this is a diagram, as you just saw here. This is the 3D drawing of that. And so the fundamental part is this Sony sensor, the wire grating sensor. I think the model is IMX250 or 264, one of them. So the camera sensor itself supports up to 30 frames per second, as they claim. But after this company Lucid did this packaging, assembly, and all that, convert into the camera that provides an API for us to program on, then the frame rate drops to what they claim is about 20. And eventually, after we did all this and based on our test, it's somewhere between 15 to 18. So these sensors have different linear gratings, and they had composed of 0, 90, 45, and 135. And each of these 4 composed of one calculation unit for different directions. So what this means is for the 0 degrees gratings, only the 90, well, let's not make it that confusing. We'll just say for the 0 grating, we have only the 0 degrees light as intensity 0 transmitted. And for the 91, we only have the 90, and 45 and 135 as the same. So with those intensity rating, so after the capture image, this is just a gray image. You have different intensity: 0.7, 0.5, 0.4, 0.3. I used all this intensity. We can calculate what we call the Stokes parameters. So the Stokes parameters is what we use to describe the completely states of the polarization for light. And in our case, because we don't have circular polarization, either in the model or in the sensor, it's not able to do that, to detect that. So we don't have S3 in this case. We're only looking at the linear polarized part, which S0 is actually just the intensity of the light. S1 and S2 describe the linear polarization states. And we could calculate the DOLP using this. So, clear drawing. And here's some examples of why we want to use this and how is it beneficial for us. And we look at this special example. Of course, in our test, we're trying to find the specific targets. We also have all the other heliostat done, but as this technology eventually, if it's going to put into the application phase, you can have all this up. So when we look at this scenario, you're looking at these two heliostats, right? Then this top edge of the front one and the bottom edge of the back one, or not just the edge, probably part of the mirrors here, they can overlap with each other, and they are both blue, similar intensity. Now this is difficult for the visible image to find where the edge is, which is also crucial for the edge detection, and then the optical error calculation method works. So comparably, in the degree of linear polarization image here, we do see a little difference. The color may not be that different, but the values can be more distinguishable than this. And why is that? Because we're taking this almost at the same angle, right? Why do we see it differently on the polarization image? So it's because of this. When we look at the remember we have the Rayleigh scattering model describe how the skylights have this pattern of DOLP differently at different part of the sky dome. So these two heliostats are actually facing when our drone or the camera look at here, they're actually facing a slightly different part of the sky. So their instant is a little different. And on the simulation diagram here, because it is 0 to 360 is azimuthal angle, and 0 to 90 is the zenith angle. They correspondingly to different part of the sky. And the key thing here is we want them to be facing the part of sky that has a high oh, I shouldn't say facing. It'd be reflecting according to our UAV position, the high DOLP region. And at the same time, we want them to have a higher DOLP gradient, which means the DOLP is changing pretty fast in this region. And as if it's changing really fast, the slightly angle difference of these two heliostats will result in that they have different part of the instant light has initially a different DOLP input. And F here is how it looks like on the reflection. So they have a different input initially that results in a different DOLP that's captured by the camera. And of course, here is a little bit detail on how we calculate that reflection. In theory, we use this thing called the reflection mirror matrix. So if we describe the input Stokes parameter as I, which is composed of what I showed before as 0, S1, S2, S3, and we have this mirror matrix for reflection, and times together we get the reflection. What's the Stokes parameters of the reflected light? And there are a few details here. We have the RL and RR, which is corresponding to the parallel and perpendicular to this interface, the reflection coefficient, and they're related to the refractive index of the material. In our case, it's the air and this mirror surface or the glass. And theta A and B are the instant and reflected and the reflection angle, which in this case, theta A is pretty much equals to theta B. So, and for the specular reflection case. So these are we actually a summary of these results were published in the Solar Paces talk I gave in 2022 and the following proceedings. And in total, we took about 708 of these images for the sky versus sky scenario. And using the degree of linear polarization, we have successful rates, which means we can detect this edge that's overlapped about over 91%. And the reason sometimes it fails is because if we are, right, it happens both of the mirrors are facing a very low region of the DOLP, then not only they won't have much difference, they also won't have much difference to the background. They will all be really dark blue. So here is the pseudo color from 0 to 1. Is the jet color map. So they will also look the same. So there will be no intensity difference. Sorry, no DOLP difference in that case. And those are the cases we failed because we didn't find a good position of the camera. All right, so moving on. Next one. Next scenario, we call this ground versus ground. Now, this is a scenario where the drone is relatively higher in the sky and you kind of look down. And now that your reflection of the ground and the actual ground are adjacent to each other and they have very similar color and intensity, this will also cause a problem to find some of the bottom edge or the side edge for the heliostats. And in this case, we use angle polarization. Now you can see that this in the visual image, these are very hard to tell where the edge is, especially for machine vision as a pointed here. But in the angle polarization, the heliostat appear to be have a very different AOP value, angle polarization value than the ground, actual ground. So here's another example. This edge here, and comparably with this edge here. And the reason for that is after the light is reflected off this rough ground, the angle polarization actually changed quite a bit. And here are some simulation examples specifically for these two images, for this image. The ground reflection angle polarization and the heliostat reflection of angle polarization, and they have a very distinctive difference. And the theory we did that, this is of course, it's a simplified approximation model. What I developed is called the Torrance spiral model. Now we see the rough ground as a random, uh, as composed of a lot of this randomly placed microfacets, and I'll calculate the reflection as if it was specular reflection for each of these these microfacets, and altogether the integral, the summation of the results will be the actual results of the diffuse reflection. So what the Torrance spiral model says is that you draw this from a Gaussian distribution, which means we're looking at this ground, we don't think it's too rough, right? We still think it's walkable. So most of the surf microfacets still have their surface normal very close to 90, which means they're flat. The surface normal is pointing up. And it's not very likely for the zenith angle to go close to 90 degrees, which means they're completely vertical. So in this case, I did I think 1 million microfacets for this calculation and this is the reflection you got. And figure D here is showing some of the, so not only this one set of images, we took this the image of this heliostat from different kind of angle. So there are 7 of them. And there's all the major difference and predicted difference are talking about the difference between the heliostat and the ground. And you can see they are all pretty distinguishable. They're higher than so because AOP is a value that's on the scale from 0 to 180, even though it's not accurate as we did all these assumptions, it is sufficient for us to find certain angles where the heliostat will have a difference from the ground. All right, so similarly, we did that. Also, the preliminary results was published in several pages proceedings. In these cases, about 89% success rate. And another thing we also find is you can also use the polarization imaging to help find the cracks. Now this image turned to be blurry because we're a little too far away from the heliostats, and this cracks are relatively quite small. But when you look at them from so this is earlier work where we have a GoPro camera right on top of the polarization camera. So when they take these images, they are at the same angle. And when we zoom in on this, we can see that there are some of these edges missing in the visible image that you cannot be detected by the edge detection. It's because to see these cracks, the cracks actually forms a scattering, and to see these cracks, we're kind of relying on the sunlight relatively angle to be correctly reflecting the overexposed points, the sunlight directly into the camera. Then you can see their shining point. But there's not a big problem for the polarization because these cracks all decrease because of the scattering. They all decrease linear degree of linear polarization. And if we can we can find the angle where the heliostat mirrors are reflecting the high DOIP region, we can distinguish these cracks from the non-cracked region and see in the edge detection of this, we see a lot better features than the visible image. So moving on, after we did all this, right, we figured, okay, now we're confident we can design a flight path that take advantages of all of this. So of course, conventionally, you still have to design the flight path as it is. There's factors to consider, like it had to be safe for the field operation, right? We cannot get too close or too low, and they have to be these waypoints need to also do the original UFA scan. And on top of that, we add in the our flight design for the DLP and the AOP to be effectively tell the difference between the overlapped edges of the heliostats or the heliostat edges to the ground. So here's an example of the captured image. Now we have the heliostat 7E3, which means row 7 and column 3 to the east of the center, which is a tower. So we capture the DLP, raw image, process it into DLP and the AOP images. And here are a few simulations related to all that. The reflection of the heliostat, the reflection, DOLP and AOP, and the reflection of the ground. And we can see that for the DOLP, you can, sorry, this is no sky versus sky. So the DOLP is not really in play here. The AOP image, you can find that heliostats very distinguishable from background. And for the DLP, actually, it also helps you to detect the edges for each of these target facets. So we're moving on. Did something similar to the U facets, not exactly U facet because we only have this one image, but we took took a similar approach to calculate the optical error. And the first thing we do, we need to crack some of the data we have here just because there's inaccuracy of the GPS, inaccuracy of the field operating, where we tell the heliostat to stop there, or we'll take the image. So the first thing we cracked is the camera position. And this is similar to a photogrammetry method that we look at the four corners of the heliostat and we can back calculate it based on the position of the heliostat, orientation, and the camera. So after that, we did a correction of the orientation arrow. So this is related to what if when we tell the HE3 to stop here, it actually moved a little bit more, orientation will be a problem. So we also use a similar way to calculate if there's a relative orientation error between these two. And eventually moving on to the U facet, we can calculate the canting error of each facet. So with that, comparable, so this is our original U facet images. This is our polarization image when we overlap the calculated mirror facet with the captured mirror facet. We'll use the diagonal line, we find the center, and with the center, we find their difference to back calculate the canting error of each facet. And the problem is we don't really have a ground truth to compare to. So what I did is we asked Randy for this design data for this field, and this is one on 83 how it designed should be. And I did a parameter fitting to find a parabolic shape according to this facet orientation. And we compare these arrows, we compare the results of what we got to the ground truth of this, which then we calculate the azimuthal arrow and the zenith arrow rotating on these two directions for each facet. Here are the results. We got about less than 10 milliradians arrow. All right, so in conclusion, this polarimetric imaging, it adds benefits in the contrast enhancement to the conventional imaging, which makes it faster, more efficient, more accurate. And we don't see this serve as a technology that operates independently, but rather it can be combined with other imaging technologies, can be image fusion to help with the field inspection. All right, so move on to the part 2, which is the mirror stalling detection. So here, the background, I'm going to talk real quick. We're not only limited to the mirrors, but this reflective surface are commonly found in research industry and even everyday life. And of course, the stalling, when it gets dirty, will decrease the efficiency of its reflection because now the solid particles cause scattering, and it will cause problem for all different kind of applications. But in our case, we mainly focus on this CSP plant. And conventionally, this is actually Randy, and this is Randy, this is me. We were standing on boom lift, taking measurements with this 410 solar reflectometer from Surface Optics. Now, having experience by myself, I can tell you this process is very difficult and tedious because this thing has a the collection angle is limited and the area it can measure is very small. It's less than 1 inch in diameter. And when we take this measurement for accuracy, we take repetitive measurements 3 or 5 times, which means, well, each time when I click the button, it goes for like 7 to 8 seconds, 10 seconds. And during that whole time, I have to hold my hand against that heliostat surface. And of course, when we check our data afterwards, we find there's a bunch of them are completely random, completely not useful because probably my hand shaked during that. Just by that description, you can tell a lot of problems with this conventional method. My really small area, accuracy, I can't speak for it, but it's definitely a lot of manually introduced by human, a lot of errors there. So imagine if we could do this, instead of taking points on this mirror surface one by one, if we can have a drone and take images and immediately tell you how dirty they are, what's the soldering level, what's the relative reflectance, that'd be great. That will make it much easier, and you will save a lot of money on labor. And the idea of that is based on polarization imaging. And we imagine this scenario, if our input of the light is a highly linear polarized light, then let's say if this reflective surface or say the mirror is clean, then after its spectral reflection, it still maintain that highly linear polarized light. In our words, it's still the high DOLP, which this can be calculated by the reflection mirror matrix I showed earlier. But if there's solid particles on the surface, which cause scattering, and now it becomes a diffuse reflection, and this will be what will cause is of course, this light will go into different directions, but also it becomes unpolarized, which means it decrease the degree of linear polarization. And we can say, okay, if it's 30, it decreases DOLP. If it's not 30, it's still high DOLP. And that way we can find a way to kind of correlate these two, the degree of linear polarization and the reflection, and then further the soldering level. So in the lab, of course, we can create this linear polarized light by using a linear polarizer. But what we want to do is we want to fly this drone over the field. Of course, we want to have a light source that's natural. And luckily, we have that, as I described. Due to release scattering, you have this pattern of the sky, and you have the high DOLP in certain regions. And this is, again, what I'm showing here is, again, the simulation. So the problem is how we describe this qualitatively, but how do we quantitatively determine the relationship between the reflection and polarization. And we're gonna start from a simple case. The first is the clean reflective surface, which is spectral reflection, which I have described it to you earlier. And another scenario is your mirror might not only have one layer, could have, like in our case, this small mirror samples we purchased and used for test, they actually have two layers, glass layer, silver polish, which means not only it has the reflection, also has the transmission and then reflection. So two different kinds of scenarios, but both considered as spectral reflection as the result. So there, the transmission we can calculate using transmission mirror matrix, similar to the reflection, both describing how the Stokes parameter change after transmission or reflection. Oh, which means if you're, of course, you can do this calculation by yourself. If you have a different structure of your mirror, you can increase the layer, you change the refractive index of each layer's material. That's this whole calculation method is still valid. So now we consider the solid particle. Uh, uh, so the solid particles are mainly like you can see them with your eyes. So they are actually similar, or most of them are larger than the wavelength, the diameter, the size of them are larger than the wavelength of the light, visible light. So in this case, we use mean scattering theory to calculate them. And now imagine we have a solid particle, and when when the light comes in and gets scattered by the solid particles, mean scattering happens. We did a Monte Carlo simulation here, and there's probability, more likely it's a forward scattering. Not very likely, it's going sidewards or backwards. So different scenarios. First case, if the scatter light goes above the mirror surface, then it's just one scattering process, single scatter. And then another case, after the scattering, it's a forward scattering, it goes below the glass layer, then have transmission reflection as calculated before. And of course, for the parts that's not covered by solid particles, we just calculate the reflection directly. So the miscattering itself also will change the polarization, and how that changes for each single scattering event could also be calculated based on the size of the particle, which is correlating to the scattering cross-section, the material, which is correlating to the refractive index, and the input Stokes parameter, the input states of the light. So this is the model that's introduced by Zuber in our solar phases conference proceedings. We're considering two parts of the light. One is the sunlight that gets scattered by the solid particles. One is the skylight that gets reflected by the clean part of the region. And in total, we can describe what's the light going to be captured by the camera. It's the sunlight scattered times the area that's covered by the particles times the ratio of the sky of the sunlight. And again, the skylight reflected by the clean part of the mirror times this area, non-particle clean area, and the ratio of the skylight. And we define the relative reflectance, which actually is the parameter we care when we are doing this kind of inspection for the mirror solidly, because we want it to be as highly reflective as we designed to be. And now that's designed as, depending on the camera collection angle, that's defined as the solid S0 is the intensity of the Stokes parameter, the first term, and the solid divided by the clean part. So one parameter we didn't cover is what's the K sun, K sky. When I say the ratio of the sunlight and skylights, how do we find out? This is related to the weather, related to how bright the sun is at that day, right? If it's cloudy, skylight increase, sunlight decrease. But how do we find that out? It's not like we can look up to the sky and just magically figure it out. So in our case, we did a fitting. Now, when we look at this, there are a few more details. So what we do is we did a azimuthal scan using this part of the sky that has a high DOLP region. And as the soldering level increase, the reflection decrease for 4 different regions with different soldering levels, you can see the overall the degree of linear polarization decrease at the camera collection angle about 10 degrees here, and from a different azimuthal angle as the camera moved in this direction. And of course, there's a furthermore correction that need to be considered, which is the different part of the image we captured can be related to different part of instant of the skylight, which also will be considered later. But the idea is by doing this, we find out that if we change the sunlight and the skylight ratio, this curve of the how the DLP is related to the reflectance is going to change. And we need to find what we need to do is we need to first measure a reference sample and figure out for that day what exactly for that day, that moment, what's the sunlight to skylight ratio. So after we did that azimuthal scan, of course, we acquire the image with the highest DOLP. And then we measure the reflectance of these 4 regions. Oh, sorry, by the way, these samples are created with 4 different regions of 4 different soiling levels. So this highest DOLP region is the cleanest, and it goes dirtier counterclockwise. And then we did the fitting, we find out, oh, the minimum error we find is when the sunlight to skylight is 83 to 17%. So we'll see, okay, that's the curve we have for that day, that moment. As time goes, of course, after half an hour, weather condition might have changed. We need to do this again to ensure it's the best accuracy. Okay, so we have this sample under test. After we did this fitting this curve, we have the sample under test measured in the same way of the DLP and the reflectance and compare with its predicted reflectance from this curve. Of course, we don't just measure this one sample. We have all different kind of sample. We have Sandia sand, Sahara white sand, Sahara red sand. They all have different particle size distribution, which will, as a result, will cause difference in the results for the scattering calculation. And here is a one set of example for the Sandia sand. We have reference and 2 sample under test. So as a summary, after we use the reference sample to find this curve, we also put the sample under test next to this curve and to find the relative error of each measured point. And again, we repeat this for different samples, so here are different sands, and the heliostat is also the Sandia sand, but it's actually a heliostat sample Randy sent to us. So if we calculate this error as the model predicted reflectance from the DOLP image minus the set of measured reflectance from the image, then we have the mean absolute error all under 3%. Here are the summary results. And the idea is with this, after you fit this curve with reference sample, we can directly translate that into a reflectance. So for the operator, you can directly see this image and determine, oh, this is under 80%, time to clean it. And of course, to further mimic the real scenario in the field, we did a tilted mirror measurement. And this tells us that when the mirror is tilted, the simulation have some zenith angle that is above 90 degrees. That's the scenario where your camera could be lower than your mirror and you look down. That's also a possibility if you're not using UAV, but with a portable imaging setup. So again, the error find here is and 3.6% is the largest error we find. So here are some results I'm going to show quickly. I think the time is running out. Yeah, so we have this 3 sets of data, a different heliostats on the same day. And before this test, we asked Randy to clean the center faucet and have this facing up at different days so they can get different soiling. And we measured the certain points with the reflectometer as I showed in the very beginning. And we comparably fit this data points with the curve at different heliostats. And overall speaking, we have this mean absolute error under 4%. And because these are all same type of heliostat, same type of sand, if I conclusively include all the data points, we have a 3.09% mean absolute error. And again, here is another approach we tried. We could have the camera looking up to, but of course, since now you're too close, we can only look at one faucet each time. And then we have some results here. It's not very accurate because this is a measurement that's close to the sun to the sunset, and making it very difficult to find the correct position to measure this. So in conclusion, we have this model to not only qualitatively but also quantitatively describe the relationship between the polarization and the reflectance, which can be used for inspecting this soiled mirror surface. And with this a quick reference sample measurement, then you can do this large area scanning with UAV, which is very fast. And it also not limited to the CSV field. It can be adapted to other field, and might need a little more characterization here and there, but the method itself is not limited. So yeah, that will be the end. Here's a acknowledgement for some of the folks helped us in the lab, and Dr. Fang Li helped us create a sample. And from Sandia side, we have Maddie Huang help me collect the soil sample. And Louis, Zach, Anthony, Kevin, the other Kevin, and George help us with our flight test at the Sandia NSTTF. And this work was supported by DOE under this grant. I think that will be the end. Thank you all.
Thank you so much, Mo. That was a great presentation. So
Thank you.
now we have time for one to maybe two questions in the remaining minutes of today's seminar. Feel free to unmute and ask directly, or if you're unable to do that, feel free to type them in the chat and I can relay them.
Hey, Brooke, this is Irini. I have a quick question. First of all, thank you, Mo, for the presentation, really very informative. So in the first part of your presentation, you referred into wireless communication of the drone with the central station in order practically, my understanding is that you send the pictures that you collect in a real-time manner to the central station. Is this correct, my understanding? Yeah.
This one, right? Yes. So so what the operators see on the GUI on this small window here is the live view of what the camera is seeing, and that help us to determine if it's the correct time to take the image.
I see. So do you have an idea of the volume of the data that you are sending? You are sending images or video?
Yeah, so we actually to make it faster, we cropped the image here. I can't really say the size of the image, but when we save the image, we save the full resolution, and each image is probably around 1 megabytes.
Okay.
Yeah.
Cool. Thank you.
It's a PNG image.
But essentially you're streaming it, right? Like we have like a 20 frame per second.
Yeah, theoretically. So yeah,
Mhm.
15 to 18 is what we observed.
Thank you.
Yeah, no problem.
There's one in the message.
Oh, chat.
See one in the chat, I can read it aloud. From Derek, polarization and wavelength sensitivity, risks of making interferences about reflectance losses over full solar spectrum when we are presumably only looking at polarization on a silicon sensor. For example, no more than 1100 nanometers.
Yeah, I think he's talking about the mirror soldering, right? Yeah, because I understand, because the most part of you have a large part of the energy of the sunlight that's the wavelength not visible. The idea is for this method is we don't need to know exactly how much energy it is related to. We're trying to find how much of the reflectance decrease as your surface gets covered by the soldering particles, which means okay, first of all, the sensor, of course, is only working in a wavelength that's probably lower than 1,000 nanometers. And with in the calculation of the model, we are also only considering the visible light. So the idea is we're not calculating the absolute change, the absolute value of the energy, or say the absolute value of reflection. We're calculating comparable to the clean part of your mirror. What's the relative reflectance of the other part of mirror? So we're actually defining this as 100%. Sorry, different color. Defining the clean part to be 100%. Even though, physically we know it's not 100%, but we know what we know is this is the clean region, the clean status we want to reach for this field. And as it gets dirty, the DOLP decrease, and at a certain point, we see this, it's under 90%, at 8%, we know, oh, it's time to clean. So it's application based. Yeah, I don't know if that answered your question.
I think this is a very good question because I think I understand because the solar spectrum we're looking at is much broader than a visible sensor. Yeah, sure. So it's much so then in this case, I think when we are doing the modeling, we can actually think it this way. So the mirror selling is going to have the level of scatter, like coverage of scatters, right? So that is going to, on one side, link to the reflectance of a whole solar spectrum that we can actually model this results. On the other side, it's going to actually link to the polarization state we can visualize with a visible camera with the polarization measurement capability. So in this case, yes, it's possible to use a polarization image that's visualized by a visible camera, but actually try to link to the reflectance of a much broader spectrum because we can actually, when we do the model, we can take that into account. And direct, yes, I think we can follow up with the discussion afterward. Thanks for the question.
Great, thank you. Thank you, Mo, and thank you everyone for the questions. In the last minute or two, I will go ahead and say a few words to wrap up. I'm going to share this, steal this screen share. And all right. So just as a reminder, the past presentations are available on our HelioCon seminar webpage. More resources can be found on that webpage as well. And then to subscribe to the seminar series or just to get in touch in general, feel free to use our email address. Our next seminar will be on November 20th with Professor Greg Kowalski from Northeastern University. So there will be an invite going out about that soon. So let's give one more round of applause to Mo. Thank you so much again for the presentation. And thank you everyone today. We will see you next month.
Thank you.